And we're back to talk more about the electrostatic force. We learned that the other day that positives repel positives, negatives repel negatives, positive negatives attract. Matter's electrically neutral in general with equal amounts of each charge, not like no charge at all, but equal amounts of positive and negative, which helped us explain this phenomenon where if you had a charged object near a neutral one, you ended up getting a net attraction. Now, you wouldn't think so because you'd think that the attraction and repulsion would balance out. You know, these are repelled, these are attracted. But you probably remember what happened. A little bit of rearrangement happens. Maybe not this dramatic, but to some extent, the ones who love these positive charges snuggle over closer, and the ones that don't like them anyway get further away. And there's a net attraction, which means love wins, not because it's inherently stronger, but because the beloved get closer together, and distance makes the heart grow less fond. The further apart they are, the weaker the force. This reminds me of something. Reminds me of when we made this big deal about gravity, you know, F sub G equals G, M1, M2 over R squared, talked all about that. And now we have a new force, the electrical force. Same general theme, you know. It's equal to some constant times something called Q1 times something called Q2. And while I didn't prove that there's a square on the R, experiments can be done. We're not doing them, but experiments can be done to prove that that indeed is a square on the R. So it does act like gravity does in that sense. Actually, the reason for both, to go a little deeper, is because influences that result from a point, like a mass right here, a charge right here, influences kind of spread out in three-dimensional space, like on a big sphere, you might imagine. And if you double the diameter of a sphere, or the radius of it, you quadruple its area. So it's thinning out the effect. And maybe we'll talk more about that later. But in any case, so we have this new equation, this law, a universal law, presumably again, kind of like gravitation, only now it's about this other thing we call charge. Now, you can't see charge. It's not some particular color or doesn't smell like anything. You know, how do you know it's there? It is our way of making sense of the behavior of objects. We attribute to them charge because it explains their behavior. So we think it's real and that things have it. So the first question I guess we ought to ask is, what the heck are the units of this charge stuff? You know, you got these two charges, say a couple of positive charges. Q1 is one of them and Q2 is the other. And they're separated by a distance R, and this is the force of repulsion between them. But what units do you use to measure charge? Now, if this were a live class, I'd make you guess. In fact, I'm going to pretend I'm making you guess. Try to think if you've ever heard of units for electric charge. You know what most people say? Most people say volts, because they've heard of volts. It ain't volts. Then some clever student says amps. Nice try, but nope. Watts. Nope. Really, really well-informed students might say ohms, but it isn't that. Then what the heck are the units of electric charge? Well, they're actually called coulombs. Maybe you've heard of a coulomb. Maybe you haven't. Well, until now, you have now either way. Named after somebody named Mr. Coulomb. And I've forgotten his first name, and I feel a little bit bad about that. You know, he did all this hard work, and I don't remember his first name. I know Newton's first name, Isaac. This guy, I forgot his name. But the unit is the Coulomb, but so's the law. It's called Coulomb's law. This is Coulomb's law, and these are measured coulombs. So we did get honored in a couple of ways. Now, a coulomb is an amount of charge. Is it a lot of charge? What would that even mean, a lot? Well, let's think about mass. The units of mass are kilograms. Is that a lot of mass? Yeah. You know, there's a kilogram mass made of metal in the room, not like that. You know, it weighs a couple pounds. That's manageable. You know, you can conceive of that, try to accelerate it. But what's a coulomb? Well, I'm going to tell you that it is a truly frightening amount of charge. If I were charged up with a net charge of 1 coulomb, I'd be like the evil emperor in Star Wars, like, you know, shooting lightning bolts at everybody, killing everybody within so many feet of me. That'd be scary if I had a coulomb of net charge. It's a huge amount of charge. Lightning bolts, terrifying lightning bolts, do transfer more than a coulomb. Like maybe a really big lightning bolt, maybe 50 coulombs. That's still a lot. I don't even want to get hit by a 50th of a lightning bolt. So why do we have such a big unit? You know what? That's a long story that I'm not going to tell right now. Historically, it got defined kind of backwards from the ampere, maybe more on that later. But anyway, a coulomb is a scary amount of charge. Now, in a way it is, in a way it isn't. It's a scary amount of net charge to have an excess of a whole coulomb of positive charge compared to negative charge. Now that's scary. To have a coulomb of positive charge and a coulomb of negative charge, heck, this pen probably has that. I've probably got, I don't know, I think I figured it out for like hundreds of thousands of coulombs of maybe something like that of positive charge and almost exactly that amount of negative charge. That Van de Graaff generator that you saw me making my hair stand up and everything, the charge on that was probably some fairly like about this many micro coulombs, millionths of a coulomb. It probably only had like, you know, 100,000th of a coulomb of excess charge on it. And it was popping pretty good. And, you know, don't do this at home. I didn't. I did it at school. But anyway, so a coulomb's a scary amount of charge in a way. What about this thing K? It's a constant, kind of like big G is a constant. K is a universal constant. We think it's true all over the universe. Its value is pretty easy to remember. It's one of those things that's so close. Well, I'll tell you what, it kind of precisely, it's 8.99 times 10 to the 9th. Let's get the units here. It's got to give you newtons, so it's got to have newtons in it. It's got to cancel out some squared meters, so it needs to be Newton meters squared. It's got to kill off these coulombs, these 2 coulombs here, so it's Newton meters squared per coulomb squared. But you know what? If we can round 9.8 off to 10, you bet we can round 8.99 off to 9. Even doing that in the AP class, we still rounded off to 9. 9 billion. 9 billion Newton meters squared per coulomb squared. So now we're going to use this equation for the very first time. It's easy, especially with the numbers I'm about to give you. So the question is, what is the force of repulsion between 2 positive charges? Each one, 1 coulomb. Each one, 1 coulomb. Again, that's scary. It's all a charge. And they're separated by 1 meter. You can do this math in your head. 9 billion times 1 divided by 1 squared. 9 billion. 9 billion newtons. And a newton is about between 1/4 and 1/5 of a pound. If I remember right, I think I figured it out before, 9 billion newtons is like 1,000,000 tons. 1,000,000 tons. That's like, is that more than the weight of a cruise ship? It's that kind of force. So a coulomb here and a coulomb here, wow, like Titanic, literally forces between them. So it is a lot of charge. And the forces between things that are just, you know, like picking up little bits of paper, that's just teeny weeny little fractions of coulomb, you know, like less than millions of a coulomb maybe of that charge doing that sort of thing. So in any case, there's our fundamental law. And of course, I can give you problems. Obviously, you can plug numbers in. I can give you different numbers of coulombs and different distances apart, and you can calculate the force between them. So that's good. I do want to note something, though. This force is fundamentally incredibly strong. And yet, I had to come up with special equipment to let you just see teeny little effects, like little bits of paper doing things, a rabbit burr going back and forth. Almost like this was just a little tiny thing to spice up the world just a little bit. Whereas gravity creates worlds. Gravity molds planets together. It makes the stars shine, controls the fate of the universe, keeps you grounded, makes the air have pressure, all that. So gravity does all these amazing big things. And all the electric force can do is little party tricks. Or maybe make that light stay on, however that works. Currents involved there. But look at this constant. This constant's big, 9 billion. And this one was 6.67 times 10 to the minus 11. Actually, if you compute the force between, say, a proton and an electron in a hydrogen atom, let's say, you'll find that the electrical force is vastly greater than the gravitational force between them. Electrons don't orbit protons like planets orbit the sun because of gravity. Gravity's got almost nothing to do with it. I hope my video didn't just freeze. I looked frozen on the video.